All right. Okay. So I would like to welcome everyone to 477 Introduction to Algorithm. My name is Tachapol Saranurak. I'm an assistant professor here working on algorithm design. And so today, it's gonna be kind of easygoing. I will not teach any real thing. I just give a teaser of a lot of things and tell you a bit about logistics of this class. Okay, and so the first thing is that so this is like a field theory class. We will motivate why we study some problem, define a problem, then give you some intuition why, state a theorem, give you some intuition why that's true, and prove that. It's just that, and there is no programming. And the overall thing in this class is that we will just learn about generic method on how to design efficient algorithm. The hope is that when you learn the way of thinking, the generic method from this class, then you can apply it to your own problem, whatever it is. So it's not going to be domain specific to anything. But the topics that you will learn in this class, the first thing is a classical stuff, which is divide and conquer, dynamic programming. So this is the thing that you might see and need to solve in a programming contest and maybe a interview question from Google or something like that. But there's gonna be some way beyond these kind of topics, and you will see. One is amortized analysis, and that is you will see what it means soon in the class. The next big theme in the class is how to use randomization for big data. Nowadays, the data is so big, and the computation task that you need to solve is huge, and you just need something that is so efficient, and the very powerful way to deal with that is to use randomization to toss the coin, and that's one big theme. And the next thing is the linear programming. This is just a way to a framework for capturing so many problems that you care about into just one generic framework called linear programming. You will learn a bunch of concepts related to that and some algorithm that you can design once you know the concept of linear programming. The last thing is how to deal with uncertainty. That is, normally when you see a classical way to compute things, you have some input, the whole input, you just need to sort number or find the maximum number or something like that. So this is a classical way, but nowadays there are many situations where you don't even know the input, and you need to decide on what you need to do right now without knowing the future input. And you want to be kind of competitive to the future somehow. So you'll see what it means in later part of the class, but this part is gonna be related to machine learning a bit too. It's gonna be quite fun. Okay, the thing that I kind of expect you to have the background in this class is first just asymptotic notation, a big O notation, and then how to prove basic proof techniques proof by contradiction, proof by induction, proof by construction, okay. And also some basic notion in graph theory, what is a node, what is an edge, what is a cycle in a graph, what is a directed or undirected graph, what is a connected component in the graph. Okay, so if all of this basic terminology, I hope that basically in this first discussion session, we will have some just like a quick overview of this thing so that you can remember or you can try to brush up on this concept yourself. Next thing is some basic data structure like list, queue, stack, heaps, and maybe also binary search tree. I draw it too. BST, binary search tree. Yeah. Some basic calculus. This is not needed that much really. Basic calculus geometry, not much, but soon, like in the second class of this course, you need to know at least a complex number. What is the root of unity? Like root of unity. This is just like basically what is like the solution of this equation basically in complex number. Yeah. So try to look up a bit. We will not need the like very deep thing in this thing, and I will kind of recall very quickly in the class, but it's going to be useful if you know it. And the very important thing in the class is to learn about probability, basic thing like what is probability distribution, expectation, expected value of random variables, some tells about like a Markov and Chernoff bound. All these things like you can try to look up in this link, and by the way the slides is already uploaded into Canvas. And also just to make sure that you have like recall this thing, I try to add some exercise in the homework related to probability too. Okay. And let's go, before we go further, let me tell you more about logistics of the class. Like basically all information that you need to know should be stored in Canvas. Okay, wait here. And first thing is that we have IAs, and so Henry is here. Show yourself. Yeah. So thanks a lot, Henry, for becoming. Yeah.
I'll see you guys in office.
All right, then there is Christopher Jian. He's not here, but then there is Jonah is not here. Okay, fine. But they have office hour, and it's really encouraged. I really encourage you to to go and talk to them and go to the discussion session. Like homework in this class is going to be quite difficult, and it takes a lot of time. And I encourage you to you will need to collaborate. I talk a bit more about that soon, but talking to friends and go to office hour and ask for questions. That's going to be helpful. Okay. Next thing, if you have any question, just go to Piazza. Everything that you need to submit to Gradescope. There's going to be lecture recording for every lectures and discussion session too. I talk a bit about overleaf scribe very soon. And if you have any anonymous feedback that you want to give to me, please feel free to do that. Grading in this class, there will be 50% will be from homework. There will be 6 homework. 20% from the first exam and another 20% from the second exam. And there will be another thing called scribe, which is a 9, plus 5 bonus percent. I will talk about this soon. Another percent is from cost evaluation. Okay, let me talk a bit about homework. I will not permit any late submission. Each of the homework, you will have like 2 weeks to do that. It will contain like something like 6 or 5 long questions that you need to prove things. But because we don't permit this, like I will allow you to like basically your homework submission that have lowest score or you don't submit, we will not count it into the grade. Okay? So that's give you some flexibility for that. And for each of the homework, you can actually find a friend to do with and make a group of 2 and just write one solution and submit. Okay? Or you can do in one, just by your own. That's good too. But in any case, working with your friends is expected and strongly encouraged, because I think when you try to come up with a proof, try a bunch of ideas, it's just good to talk to people. It just makes your thinking clearer, and maybe just you let your friend help you too. Okay? But in any case, each group must write the solution independently. So if you don't do that, there's going to be some problem. And yeah, submit your solution to Gradescope. And I want to recommend you to try to write your homework using LaTeX, and you can go to Overleaf to write that. If you have not tried it before, you can just try. It's not too hard. Yeah. It will help us quite a lot when to read your solution. Okay. Next is about exam. Everyone must, you cannot do it in pairs here. Everyone must do it individually. Here is the date of the exam. The exam will be take home, and you will have maybe more than 24 hours to finish that. So the goal of the exam is to make it easier than homework. It's just to make sure that you understand stuff, but it's still it might still take you some time as well. Okay, any question up to now? All right. The next thing is about scribe. This is might be the easiest way to get point in this class. So everyone just need to do the scribe for one lecture. Just do it once. Okay. So I expect a nice quality of the scribe, and basically for after each lecture, if you're gonna scribe for that lecture, you have 10 days to finish the scribe. And actually, for each of that lecture, I even will allow a group of 3 to do together to finish the whole scribe. The way to do that is to first just sign up for your slot here. Just go to this link and put your name in this Google Sheet, and then just put your name to only one lecture, right? Because there are a bunch of people here. And then once you put your name there, you go to this Overleaf project, and whatever and then I have created some template for the scribe already here. You can just try to modify that, and what you do is you create the new folder for each of the lecture, and then put some file into that folder and write the scribe together with your friend. Okay. And for this, the grading scheme for this is just you need to make it the content should be complete, and it should be clean and nice style, and there will be a 5% bonus. That is, if you find that the lecture that I give, there can be some nicer illustration, or just add more pictures, or even some PowerPoint animation, you can just say that, okay, you make some and add a link or put a picture into that scribe. if this is like something that I didn't include, or actually it's just have a better quality than what I have, then I give that to you. Okay, 5%. Okay, so, and the example of what I kind of expect, or you can just look at my previous class here. This is for another class. It's called expander and fast graph algorithm, but yeah, this is for something else. But you can have a look at the scribe of each of the lecture here, just for example. Okay. Any question up to this point about the logistics of the class? Okay, great. Now, back to this. Okay, so, and one thing about this class is that I really encourage you to ask me a question. I really don't mind any question. And if you have a question, it's really likely that a lot of other people in the room have that same question. So please just ask. And also, like, it will help me a lot if, like, whenever I explain something and you, even if you don't ask, like, if you give me some facial expression, like understand, nodding, or like, what is this? Like, it will help me too, right? Okay. Okay. And now in this class, first class, what I'm gonna do is to kind of give some, like, some kind of high-level motivation of why do we study algorithm design at all. Because the rest of the course is gonna be like kind of not as, like, kind of, it's gonna be a bit dry. It's inevitable because it's about theorem and proof and ideas. So today I'm just gonna give, like, tell you about, like, why this is important. What's the point of all this? Okay. And the first thing that I want to tell you is, like, to give you some example of algorithm that have, like, affectable significantly. And there will be, like, 3 examples about 3 algorithms. The first example is about very basic problem about multiplication. So let's go with the first example. Multiplication, everyone knows what it is. Like, let's say the problem is just you have 2 numbers. You have A and B. Let's say it's a long number, like not just like 2 digits. It has n digits, okay? And you want to multiply them. Okay, so we all learn about how to do this in grade school or something. It will take you like an n square operation. Why? Because, like, this is like your table tabular algorithm. I don't know what's the name, but right. This is just like you multiply 1 to this whole thing, you get 5 number here. Multiply 2 to this whole thing, you get this number. At the end, like if this is like a 5 digits here, you have something like 25 numbers that you need to even write down and then sum them up. So that's like a n square operation. Okay, so this is something that everyone knows. It's like a nice algorithm, not too bad, and it has been known for like thousands of years, like by some Babylonian a long time ago. But whenever we have any task, the point of algorithm design is always this: can you do it faster, right? This is basic task, but it has been done for thousands of years. But you can always ask this: can you do it better? And then, like, the history is that, like, something like 60 years ago, like this guy, a Russian mathematician called Kolmogorov, he kind of make a conjecture by giving, like, he want to give a seminar discussing this problem, and he want to get conjecture that, okay, no, this is the best. This is the best way to do it. It turns out that within a week after the seminar is announced, one of his students, Karasuba, he managed to show that, okay, actually you can do something better than n squared. The running time is something, this weird expression, which is something like n to the 1.58. Okay. And then like, this is the first improvement in thousands of years. So that's cool. And yeah, when you get some improvement, you can always ask, can you do better? Okay, and then, yeah, people can do it better. People can get it down from like just some polynomial factor here. You get like something almost linear. Now it's just n times log n times log n. And then like there will be like a more and more improvement because we can always ask if you can do it better. And just very recently, 3 years ago, even there are some improvement to this super basic question. Now it's like n log n. Okay. So this algorithm is going to be like our first algorithm that we will do in details in class. By the way, now after this work, like you can ask again, can you do it even better than n log n? Very interestingly, in the same year, another group of researchers shows that, okay, now you shouldn't be able to do it better than n log n, but they need to assume some conjecture. So this is not like maybe not true. Assuming some conjecture, then n log n is the best thing to do. And this conjecture, interestingly, is like actually a very surprising connection, because this conjecture, maybe I give the link to you, but this conjecture, it talks about some efficiency about communication, how to communicate in the network. Has nothing to do with multiplication, but somehow this connection can be made. And I want to say like this kind of crazy connection between two really unrelated things kind of happen really very often in theoretical computer science, which is like a bigger thing than algorithm design. Yeah. So that's interesting history. And actually, all of these things, all of these ideas that give you like something close to linear, this is based on some idea called fast Fourier transform. This is another, like, it's going to be in the second lecture. We will get like a flavor of this in the second class, like the class after next class. Yeah. Okay, but fast Fourier transform is really impactful. It doesn't just give you like this fast multiplication algorithm. You must have heard about this name sometimes, right? Like it has like impact in like audio and image processing. Also, it's like a very like a basic thing inside, like extension of it is like it's really in a lot of quantum algorithm right now, and it kind of discover or rediscover 60 years ago. But again, like Gauss did it like hundreds of years before. So nice story about this. But my point about multiplication is that improvement, even for super basic tasks that has been done for thousands of years, is possible if you ask that question. And yeah. And the open problem that still remains is whether you can multiply two numbers in n O of n time. That's still open. Another way to put this question is, can you multiply? Is multiplication harder than addition? Right? Because if you have two numbers with n digits, just the basic algorithm that you have learned from grade school, you can add two numbers in O of n time. But can you multiply two numbers in O of n time? We don't know. No one knows until now. Okay, that's the first thing. Next thing is I want to talk about factorization. Okay, this problem is another basic problem. It's like you have a number, let's say it's number c with n digits. just want to find two numbers A and B such that A times B is C. It's like an inverse problem of multiplication, right? So again, we have learned how to do this in school too. There's a trivial algorithm to do this, which is just like you start with C, you have C, then you try starting from 2, see if 2 divides C. If so, you're done. If not, you just try see if 3 divides C and keep going, right? And this algorithm is going to take you like 10 to the n over 2. Why 10 to the n? Because if C have 10 digits, then the size of C can be of size 10 to the n. But we do it, like we repeat this loop up to square root, so it's 10 to the n over 2. Okay. But this is exponential time. Like if you have like a 10 digits number, just 10 digits number, you need like a more than billion step. So that's crazy. That's super slow, right? Can you do it better? It turns out that people have found some like a super cool algorithm. Still not so fast. It's like a 2 to the n to the 1/3, right? Which is like which is actually, if you think about it, even like this thing is super small compared to the 2 to the n to the 1/3 when n is big enough. So this is not even polynomial time. So can we do it better? No one knows still now, until now. Should we be sad about this, that no one knows how to do it fast? Okay. It turns out that not always. So the next slide is not going to be about our class. It's going to be about cryptography, but it's a nice story anyway. I want to tell you. So the point that I want to make about one of the very cool insights from theoretical computer science is that difficult problems can be very useful. So why? So what happened is that this guy, Ribes, Chamier, and Adamant, they basically shows you that, roughly speaking, if factoring is hard, then you get like a secure internet, security of internet. Yeah. And this is also called like a public key crypto system. And if anyone have heard about public key system, crypto system? Okay, yeah. That's the point of RSA. And actually, this is really the modern theme of cryptography nowadays. That is, just assume that some computational problem is hard, then you get something magical. That's the point of cryptography in the modern days. And there are like many magical things that has happened, and people are trying to make it practical nowadays. One is like a zero knowledge proof. It used to be like a kind of esoteric notion that nowadays like people have used it in cryptocurrency. But let me tell you a bit about this. It's like a nice concept to know that it exists. So what is zero knowledge proof? It says that like it basically allows me to convince you that I know some secret. Let's say like I know, suppose I want to convince you that I know the proof of some really cool theorem. Okay, I want to convince you that I would know that proof without telling you how to prove that statement at all. And like you will not learn anything about the proof at all, except learning that I know that proof. And this actually can be done for like any kind of NP statement. So, and this is possible, assuming one-way function. So, it's a cool thing to have. Another thing is it's called fully homomorphic encryption. This is like another useful thing. Like, imagine that you want to ask something to the cloud, like to the cloud computer, but the information that you want to ask is so sensitive. It's like some private information. Like I want to know if I have some disgusting disease or something like that. So basically I wanna compute some function f of x. But what can be done is that I can basically do it using and to compute this function, it needs a lot of computation. So I don't want to do it myself. I want to ask the cloud to do it. But what I can do is that I can compute this thing in such a way that I don't even reveal what is x, and f of x to the cloud. So the cloud will not even know what is input and output, but the cloud can compute you something for you. So that's useful. And like people try to make it practical nowadays. But yeah, another point is difficult problem can be useful. At least it gives us internet security. Okay. So that's like one very cool idea from TCS. There's one plot twist that is some years ago, 20 years ago. It turns out that Peter Shaw showed that quantum computer actually can factor numbers fast. It takes just n squared time. So that's really cool, right? Like it means what? It means that if someone have successfully built practical quantum computers, then you can break internet security. So this really like sparked the new era of crypto. Like try to get secure internet against quantum computer. So this practical one doesn't exist yet, but we want to be prepared for it. Okay. So that's the second example. Let's go to the next one. It's about shortest path. So problem for like algorithm design is not just about numbers, right? Not just about sorting number, multiply things. It can be about like a large part of it is about graph, something that more tangible. You can draw it. And what is this problem? You have a graph with say n vertices and m edges, and you have two vertices s and t. And what you want to compute is a shortest path between this s and t. You want to go from s to t fast. Okay. So we will learn about this algorithm in class. Before like 1959, there's like algorithm called Bell-Manford. It tells you how to compute this in mn time. So we will learn about this later in the class. But in this year, Dijkstra actually shows how to compute this shortest path in m plus n log n time. And this speed up just by a linear factor is actually so like impactful. It really is the basis of internet routing nowadays and Google Maps and so on. So it's just improvement by a linear factor. It's so important actually. A nice funny story, I don't know, about this algorithm is actually that what happened is like this guy Dijkstra, he's like kind of go shopping with his girlfriend, get tired, and then just want to sit at a cafe, and then he said to himself he want to think about this problem, want to solve it. Then 20 minutes later, he get this algorithm without using any pens and paper. Actually, this is the way for him to like design algorithms. Like he just try to think clearly in the head and get some algorithm. That's why his algorithm is usually clean. So this is not the way I work at all. Like I take a lot of time. I use a lot of pen and paper, but amazing people are crazy. Yeah, but anyway, shortest path, like it has been shown how to do it close to linear time, long time ago. But you can still always ask, like, is there anything you can do further, right? And actually, still, like, there are a lot of exciting development until today, even about basic problem like shortest path. So one question, for example, is you can ask, if you have like a lot of computing power, like let's say you don't have just one computer, but you have so many computers, like n of them, right? Then maybe you want to speed up your whole computation by a factor of n, right? Like that's what it means by parallel computation. When you have so many computers, you want to solve your problem in parallel time, so that this parallel time is fast. But maybe the total work is big, but the parallel time is fast. You can ask this: can you do this kind of parallel computation for shortest path? So the goal would be like, if you have even m computers, like the size of the number of your computer is as big as the graph, let's say. Can you even like still compute your shortest path in total work, which is like close to linear like before, but the depth, the parallel time now should be super fast, like just polylog n. Make sense? Okay. So do this or do this. Does it make sense? Okay, thanks. Okay. So yeah, it turns out that this is not like something that is easy to see at all. Because if you see like a Dijkstra algorithm, we will learn about this, but I suspect you have seen at least once in some previous class, one of your previous class. Like, but we will learn about this in details. Like Dijkstra algorithm is so sequential. It kind of, to make like a next step, it really depends on the previous step. Like, so the sequential dependency on this algorithm is so big. Like the depth actually is n. So that's that. And no one know how to do this for a long time, how to make it better than n. And just like in a few weeks from now, actually, these people are gonna present how to improve Dijkstra algorithm so that the depth is root n instead of n. And the work, the total work that you do is still close to linear. So that's very cool. Yeah, and so SODA is like basically one of the best conference in algorithm design. Okay, so you see like even basic question, like a super recently, like something can still happen. And my point I want to make is that like so people know well like a lot of inventors that have changed the world, like Edison that invent light bulb, Gutenberg invent printing press, and like Louis Pasteur invent vaccine. And this is like they get like great credits, and they really change the world. They like create a whole industry. But this is the same, right, for a lot of other people that design algorithm. Dijkstra that design shortest path, it really enable like the whole industry. Like it enable internet routing. From Fourier transform, you get a bunch of things. From RSA, you get internet security. So these people, they are literally like they are heroes. They really changed the world so much in just a few decades. Right? So I want to like I hope that you see that like algorithm really significantly changed the world, and this will only accelerate. The field is growing faster, and as you see, exciting algorithm just keep like actively designed every year. Okay. So now, like, I want to kind of tell you a bit about my story too, like how it's like actually to be the one who design algorithm, so that like you get like a picture. Hopefully that motivates you a bit to learn stuff from this class. Okay, there's going to be 2 stories about 2 problems. For each of these problems, I will try to inject some technical stuff into it a bit, but like it's supposed to be like a easy going, like easy to listen. Okay, first thing, dynamic spanning forest. What is this? So before I define what is this problem, let me motivate it a bit. So traditional way of computing, traditional model of computation is just to solve some problem from scratch and be done with it forever. And large part of like maybe like in the first few weeks of our class, we're gonna focus on this thing too. That is, you have input, you want to compute something, you get an output, you'll be done. But actually, this static model of computation cannot really capture many real-world situations. Why? Because everything keeps changing. If you want to get like a summary of like a large network like Facebook graph, it keeps growing. Everything keeps changing. The road network, it keeps changing. Everything keeps changing. So what we need is that we want to solve like the same problem repeatedly. When the big input keeps changing, without recompute everything from scratch. Like when the input changes by 1 bit, you don't want to redo your computation from scratch. Okay. So what we want is like you have a user that has the input. The user should be able to like just tell the computer to update something, to update the input just by 1 bit, and then like you get a new output without recomputing something from scratch. That's like what we want is usually like a interaction between user and computer. Okay. And yeah, like the goal is to get something like a algorithm that is with fast update time. Like the time to return the new input should be fast. Should be faster than recomputing things from scratch. So that's what dynamic algorithm is. It's like a way how not to compute things from scratch. So, and you see, this is like a very natural question you can ask. For any problem, you can ask, if your input changed just by a bit, do you need to recompute everything from scratch? And because of this is not so natural, it really motivates people to look at this problem and get a bunch of papers from it. And what I will tell you a bit about today is this problem called dynamic spanning forest. Okay. So now I can define things a bit. So what is spanning forest? Let me first tell you what is spanning tree. So spanning tree is just when you have a graph, a spanning tree is a tree which is a subgraph of that graph, such that it includes all nodes. So for example, if you have this graph, then the red tree in this, like the red subgraph in this graph, first of all, it's a tree. It contains no cycle, right? If I add this thing, then it's not a tree anymore. But this is a tree, and it contains all nodes, because every node is connected in this tree. Okay, so that's spanning tree. What is spanning forest? It's just a set of spanning tree on every connected component. So if you have 3 connected components like this, and if each of them you put a spanning tree in it, that's spanning forest. Okay, with me? Okay, good. So now, what is dynamic spanning forest problem? Well, it's just a problem where you start with the graph, and then you want to maintain a spanning forest at all times. For example, you have a graph, then there is one edge update given to you. Like here it says delete an edge from 1 to 3. So you delete this. This tree is not a spanning tree anymore, so you need to kind of update your tree. And what you output is how you change the tree. Then after one update, then there will be a next update come to you. You insert. Here it says insert 2 to 3. But this tree is still spanning. Nothing needs to be done. You don't need to output anything. And the next update comes. You delete according to it, and just edit your tree and output what is changed. So that's the problem. Okay. So question is, how fast can you do after each update? How fast can you obtain this new spanning forest, right? Okay. So the easiest way, like to deal with this, is just after one edge update, just redo the whole computation, and you can do like any algorithm to obtain spanning tree, like do depth first search or breadth first search, and you get a tree from it. So that takes linear time. So do you think you can do better than linear time? Do you think people can do better than linear time? Should be, yeah, should be. And yeah, very natural. It turns out that like something like 40 years ago, like Fredrickson showed actually that, okay, instead of doing it from scratch and take linear time, you can do it much faster. It's like root m, square root m. So that's fast. Then like some few years after that, people show how to get root n, and n is less than m if the graph is connected. Like you will assume that m is at most n. So yeah, so that's faster. And then many things has happened. And then like a few years, my co-author and I actually managed to show that we can improve from root n to just n to the little one. So what is this? Like, just to recall you, like n to the little one means that it actually less than n to the 0.0001, right? That's what it means. So now it's much faster than root n. So so many things happens, but I would try to go through a bit about this, like so that you learn about some theoretical concept that is interesting, and it kind of go through my story too. So okay, so what happened is actually like since my bachelor, I want to try to like do some. I know nothing at that time. Like I was in Thailand. I just want to try to do some research. I don't know what it is. So I just asked one of my advisor. His name is Jitat. And then what happened is he just gave me the paper, asked me to read, and like takes me months to just absorb some little part of the paper. But it got me interested in this thing. So what he gave me to read is basically this paper, the one by Home. I tell you soon what is this thing. But yeah, it get me interested in TCS, and that's why I kind of try to do some project with him, and like nothing much going on, but still like I try to like apply to graduate studies, and basically got rejected from all places, except the place called Saarland University in Germany. So that's what happened. But now let me tell you a bit about the paper. This one. So this is a paper that is that is published in a conference called STOCK. It's like basically top conference. There are two top conferences in theory. like a fox and stock. Another one is called soda. Okay. So what they show is really cool actually. So they show that you can actually improve root n to just polylog. Okay. Polylog is something that is like a log to the C for some constancy. So that's it's way faster than root n, right? But the catch is that it has this thing called amortized update time. So what does this mean? It means that the guarantee is that after k many updates, the total time that you will take is just k polylog, k times polylog n. So it's like on average, the time is small, it's polylog. But it can be the case that there will be some update during this k updates that you take so much time, but on average it's still small. Okay. So that's kind of nice already, but basically we don't want that. We want every update to be fast. That's a natural question to ask, right? So we want to remove this thing called amortization. That's the goal. And so people try to do that. What happened is that, okay, after that I went to like a Saarland University in Germany, right? Then I got exposed to many areas in TCS. And after that, like I decided to start my PhD in the area called complexity theory. But then I have a chance to listen to this talk by Valerie King. So what she do is like she present her paper, and the talk is so cool actually. I still kind of remember, and it makes me want to do research in this area. So what's the talk about? It's basically this paper. This paper, what happened is that people said that they want to remove amortization, and this paper said that you don't need to pay like a lot of time for some of the update. You get really polylog update time for every update now. So that's great. And but the catch again is that this algorithm is randomized. It tosses a coin, and more importantly, it can make error. There can be after some update at some time, like the algorithm might return something wrong. Yeah. Okay. So although it's like with high probability that it's correct, sometime it can be wrong. So we can ask again, like, can we remove this? Right? It's not quite as good as this one that is always correct. Yeah. Right. So that's the point. Like so what happened is that, okay, I listened to this talk and like have a chance to work on this a bit. So switch my PhD program to do this algorithm design, and then try to work on this problem for a while, for 2 years, and cannot try to submit something and got to rejection. And every after rejection, we try to improve the thing further. And along the way, my advisor kind of guide me what to think next and so on. So that's really important. Like advisor is really good to have. But along the way, what happened is that I have a chance to learn, try to explore more things, like what is useful. I have a chance to learn something called expander graph. Doesn't matter to you right now what it is, but it's something that is cool. But after 2 years, then like the effort pays off. What we get is that we managed to get an algorithm that is always correct. It's still randomized, but at least it is faster than root n by a tiny bit, like n to the 1.49 something, 0.49 something, yeah. So okay, but it's the first thing that break the root n barrier without error. That's good. To my surprise, by the way, like when we announced the work, it turns out that there is another guy, which shows that okay, he can get something similar too. So that's quite crazy at that time. Like work on it for 2 years and then people can get it too. But anyway, like when we know that happened, we just like talk together. And what's very cool is that like just by talking to this guy, Christian Wolf Nielsen, and my advisor, Danupon Nong Kai, we managed to just improve from this thing to enter little one. So now it's like quite fast, very fast now. Except that, and also still have no error, but still randomized, right? So that's like a kind of already quite good now, except that it still make like some like toss a coin. We usually like deterministic algorithm more. Yeah, so what we meant to do is like to remove randomization, and basically I try to do this for the rest of my PhD and have no success. Yes?
I was wondering, how is O of 1 faster than 0.494?
Oh, this is little o of 1.
Oh.
So like
constant, right?
No, little of 1 means that it approaches 0 when n is big.
Oh.
Yeah, right. So it's like smaller than any constant.
Oh.
Yeah. Thanks for the question. Okay, good. So yeah, so what I try to do is that okay, this is still randomized. It's very fast now. Like it's kind of enter little one, so it's good. But this is an enter little one, which is still like so this is something like that is much smaller than this, but it is still like bigger than polylog. Yeah. I kind of hide what exactly is this expression in the little one, but it's something that is still bigger than polylog. So not as fast as this guy, but still quite fast now. Yeah. So yeah, try to remove randomization, but cannot do it. But yeah, after that, I was like a postdoc at Chicago. And knows a lot of great people and try to learn from them. And eventually, after almost 10 years, like we get it. We get this, make this thing deterministic. And the key techniques, again, is something called expander, something related to expander. So yeah, that's what we got. We make this deterministic now. So always correct and faster than this thing. So that's the first strict improvement for like almost 30 years. Yeah, so as you see, like I mentioned quite a bunch of time about expander. What is this? I will not actually have time to tell you, but it's like some concept that is so impactful in theoretical computer science. You can look up in the internet. But I also have like one course that's just dedicated to this thing, the whole course. Or I have a tutorial session on it too, so you can have a look if you want to. Anyway, yeah, like because it's so powerful that like you see, like I use expander thing to get this improvement from root n to n to little one, and kind of using the same framework, we managed to like get like break the decades old barrier of many other problems. So something powerful, useful to know if you want to think about this area. Anyway, until now, like I still try to improve this enter little one thing to polylog. It's still something you can always ask, right? Like, can you do better? I do that. No success yet, but maybe we can solve it in 10 years. Who knows? Point is like for me, research really take my effort, but it's really fun. Like it along the way, like you get like you see like it's like an incremental step, a lot of incremental step. Each of the step, like people like in the community really like give credit to it. Each of these steps that I publish, it get to this like a top conference in the community. But each of them along the way, at the end we get something nice, and so it's really fun and rewarding. Like this is how it's like. Let me tell you a bit about another problem. You will learn a bit about some nice concept called Gomori tree in this part. So the problem is called all pairs minimum cut. We will learn in more details what is minimum cut, what is max flow in this class. But let me tell you like quickly and in high level in this talk. So what is min cut? Well, imagine that you have underrated graph like this picture, and each edge has a weight, right? Like this has weight 7, this has weight 5, and so on. Then I said that a set of vertices is a ST cut if it contains S and doesn't contain T. Well, like this set is a ST cut. But let's say this set, this is an ST cut. Right? That's the simple definition. And like given any cut, the weight of the cut is just when you sum all the weight of all edges crossing the cut from S to outside S. For example, this cut, the green thing, the weight is 4 because you count this one, and this one that cross the cut. Okay. So here the weight is 4, and this one the weight is 10 because this is 1, 7, 1, 1. Okay. So that's the definition, and ST min cut is just ST cut with minimum weight. Like for example, this cut, this green cut actually is a min cut. Like there is no other cut that has weight less than 4. Make sense? Okay, good. So now I want to tell you a bit about very cool object called Gomori tree. Okay, it's even surprising that it exists. So informally, it's a tree that can encode an ST min cut for every pair, not just for one pair, for every pair ST. So now let me be more formal. So it's a tree. It's a tree that shares the same vertices, same set of vertices as a graph. Okay, it has the same set of vertices, but it has different set of edges. And what it guarantees is this. For every pair ST, if you look at the minimum weight edge in the ST path of the tree, that edge will correspond to ST in cut. So that is a bit of the mouthful, but let's see what I mean by this. So suppose that I want to find ST min cut. Okay, I look at S and T in this tree. There will be just a unique path from S to T, which is this path. And then I look at the minimum weight edge in this tree, in this path, which is just this guy. Now, if you think like if you cut this edge, it's gonna split the tree into 2 parts, right? But so once you split this, cut this one, you get this set. It split the tree into one side. But it will be the case that this set will exactly be the minimum ST cut in the graph. And it's going to be true for every pair. This is going to be true for every pair. For example, if I want to find dt mean cut between d and t, all I need to do is just walk from d to t, right? See which one is the minimum edge in this path. It's 3. So I cut this guy. It split the graph, split the tree into this side. It will be the case that this set is just dt mean cut in original graph. Is this clear? Yeah. Yes.
So how do you make that huge tree?
Yeah, that's a good question. That's the point. Like it exists. It's not even clear that it exists, but it does. And how to compute it is something that people care about. Yeah. It's non-trivial. But you see, like this is so surprising because there are like how many pairs of ST pairs there are? Like n square pairs. For each pair, you have like a number of ST mean cut. There are n square many numbers that is useful, but it turns out that all this information can be encoded into just one tree that has just n edges. So you can compress n square numbers into just something of size n. So that's impressive that it exists. Like now, it has some cool application in practice too. I don't know much about that, but you see, like once you have this tree, it can be used to solve many other fundamental problems because given this tree, like you can kind of pre-process this tree in kind of linear time, so that actually you can, given any pair ST, you can query for this for the number of ST mean cut in time that is so fast. You don't need to actually really walk along the path and spend like time that is linear in the size of the path. You can just query it really fast, actually. So for example, if you want to solve all pair minimum cut, if someone gives you this tree, you can just query this for every pair and be done in like something like n square time. So that's great. So that's why like there are like it's an important object, and what happened is that how to compute this. This is a good question, and like basically 60 years ago, it's like actually Gomery and who actually showed that it exists and show how to compute it in this time. N times the time to solve MaxFlow problem. So in our class, we will learn that if you want to compute one ST mean cut, you can solve it using one call to MaxFlow. You will learn this like more formally, but today, but it means what? It means that if you want to solve all pair mean cuts, you can solve it using n square MaxFlow calls. So this works already is like a kind of cool because it shows that to compute Gomery-Hood tree, that can imply that you can get all pair minimum cut fast. To compute this Gomery-Hood tree, you just need n MaxFlow instead of n square. So that's already non-trivial. So 60 years ago is a cool problem already, and then it turns out that this remains the fastest algorithm until now. Last year, I and my co-author shows that you just need actually polylog many MaxFlow calls to MaxFlow plus some additive factor. So that that's much faster than n MaxFlow calls. Yeah. And because MaxFlow can be solved now quite fast, the total time that you end up with is just instead of mn, you get n square, and actually we get something like m linear if the graph is unweighted. Yeah. So that's one of the results that I really like, and the fact that people have haven't get like this improvement, it's not because they haven't tried, but like they try and fail, but they get something only for special case of the graph. But we managed to get improvement for the general graph. So how can this happen, right? Like so what happened is like I basically read papers, try to read papers all the time, and it turns out that like this group of people, they try to like do something about Gomori Ho tree, but they use something called this. They use expanders, and I know it well, so I kind of see immediately like how to simplify the bit and improve it. But so once I see that, I just talk to these people, Jason Lee and Demaya Panigrahi, and get some partial result. So not like this final result yet, but yeah. Then once that happened, like the two group of people, me and all these people, like we join together and try to work together, and at the end, yeah, that's when we get it. Okay, so just to summarize, to solve all pairs minimum cuts, you can actually represent all of them in just n space, and that's known for 60 years. And you can construct this representation in just n squared time, and that's just known last year. Another thing that like I want to quickly mention is a vertex cut, which is just a very analogous concept. Like it's just analogous concept. So let's say that the graph is unweighted. There's no weight in the graph. Like each edge has weight 1. Okay. Then another way to just describe what is ST-min cut, the value ST-min cut, is just that you ask how many edges you need to delete so that S and T is disconnected. Right? We learned this in the class, but you might be able to just see it just from this talk actually. Yeah, so that's the value of ST-min cut. When the graph is unweighted, number of edges you need to delete to disconnect S and T. But once you put it like this, then it's just very analogous. Like it's natural to ask like about how many number of vertices you need to delete to disconnect S and T from each other. So that's called ST vertex min cut. The number of vertices you need to delete. So once you define it like this, it's just natural, right? Like to ask, is it something like as amazing as Gomori Ho tree for vertex min cut? So what's your guess? Anyone say yes? Anyone say no? Okay, so yeah, it turns out that it's a bad news. So it turns out that what we are able to show just last year is that when you talk about vertex min cut, if you want to represent all pairs vertex min cut, you must use space n square. So I showed this with Seth Petty and the student from China. What does it mean? It means that it just cannot happen that there is a Gomori Ho tree, because Gomori Ho tree has just n edges in it, right? The space for that is just n. But I said that no matter what, you will need n square space for vertex min cut. So it just cannot exist, the Gomori Ho tree for vertex min cut. Moreover, like the time that you need to compute all pairs vertex min cut, you will need like a n to the 4th time. So, and this is actually tied with the upper bound. But the point is that you see like something interesting can happen, like a concept that is so similar and both of them are fundamental can be drastically different. Like something like this can happen. Quite interesting. But I guess the point is that like there are like a lot of problems that is so fundamental and so basic, but a lot of interesting angle you can still ask and get improvement about it. Yeah, so like that's like a kind of my like interesting story. Hopefully it's fun to listen to. There are more things to talk about, but let me know if you want to learn more. And let me summarize really soon in 4 minutes or something. So I think that like algorithm design or in general like theoretical computer science like can really impact quite a lot in the future. There are like some trendy topics like ethical algorithms. So nowadays people use algorithm to like that kind of affect people's life, right? Use algorithm in hospital and that need to respect privacy. Use algorithm to decide whether or not you get into some university or get into you can make a loan or not. So that need to be fair. And this is like a hot topic right now, and people really care a lot about it. There are like a bunch of algorithmic questions in AI, like machine learning. I guess you all see like it's really like amazing right now, but one can try to make it much more efficient than it can be today. And as I mentioned, quantum algorithm is very interesting, right? So hopefully maybe I can touch upon privacy a bit in this class, but like anything else maybe a bit out of the scope. Yeah. So now like but beyond this, beyond like some trending stuff, like I really think that TCS or algorithm design can really play a crucial role at the core of other scientific discipline. Why? Well, scientific theory really like need to be predictive. And like what is prediction? It's just like something that you output. Like it's just the output of some procedure, some algorithm. And if that procedure takes like forever to compute, then it doesn't mean anything. Like it's not predictive anymore. So for the theory to be predictive and effective, it needs to be efficient. So let me give you some example. Like so Darwin, which talks about like a theory of evolution. It says that okay, everything is like all the life form evolve using variation and selection. Well, okay, this is like kind of a vague statement, but kind of believable. Like it's kind of dominating theory right now. But you see, like and by the way, I really believe in this. But you see, like human genome is so long, like billions of bits. How long is the Earth? The year, like how old is the Earth? Well, just billions of years. So it's just the question is that how exactly that the nature can discover this amazing genome of length billion of bits in just 4 billion years.